Okay, this is part 1 of our calculus boot camp. We're going to talk about derivatives. So first off, what's the point of them? Well, the whole point is to find slope. You already know how to find slope on a nice, easy graph like this. So we're going to just practice that for a second. Remember that slope is always rise over run, or the mathematical way of putting that is delta y over delta x. The change in the y coordinate divided by the change in the x coordinate. So if I wanted to find the slope of, say, this section here, pretend it's straight, sorry I don't have a ruler on this thing yet, I would find, well, it rises a 1, 2, 3, and it runs 1, 2. So the slope would be 1.5. You can also leave it as an improper fraction. I'm good with that. If I wanted to find the slope of this section here, oops, and sorry, I tend to talk to myself when I'm waiting for my hand to catch up. Okay, I got a rise. Well, it's down, so it's actually a negative rise. It goes down 2, so it's negative 2, and it runs 1, 2, 3, 4. So the slope is negative 1/2. Well, that's all well and good, but what if you have a function that is not a nice straight line like that? What if you have, say, a parabola? I'm going to pause this for a second and draw a parabola. Okay, and we're back. What if I have a parabola? Well, I have a problem, because the only place I can readily find the slope is right at the top, because I happen to know that right at the top the slope is 0. But what about if I wanted to find the slope, let's say at negative 3, x equals negative 3. What if I wanted to find the slope right there? I can't really, because the line curves after it and before it. So I can't really find 2 points to do a change of y and a change of x. Now, I guess I could estimate by getting a ruler out and trying to make a tangent line like this, sorta, but that isn't really kind of like that. And then pick 2 points on it and do a rise over run over, like over on the left. But that's not very accurate. I could get an estimate on that, but it's really not accurate. So instead we have this thing called a derivative. The way that we'd write it is dy over dx. That's going to give me the slope at point x. The slope at x. If you look at it, it's kind of close to this one, sort of. In fact, if you just changed the triangle to a d, it'd be exactly the same. And there's a reason for that. See, the triangle is a delta. Starts with a d, doesn't it? When you use a d, it's kind of like you're doing change of y over change of x, but just a really, really small change. What we've basically done is we've said, okay, I want the slope at that point. I'm going to start out here, and then I'm going to get a little bit closer. I'm gonna bring the ends of that line that I drew in closer. So maybe I'll just do a line from there to there, and I'll get closer. It's kind of like when you're sneaking up on a cat. Get closer and closer, and soon I get so close that the changes are, we call them infinitesimal. The changes are so tiny we can't use the triangle anymore, so we use a d. I don't know if that makes any sense at all. Ask me tomorrow if it's really confusing, or tell me if this is working. This is really hard without any student feedback. So the way that we get this is a pretty simple little trick. When I want to find the derivative of a polynomial, so I've got a nice little polynomial right here ready to go, there's a very, very simple trick for this. So I want to find the derivative of y. In this case, y equals negative x squared plus 9. So I'm going to replace that y right there with parentheses negative x squared plus 9. Come on, plus sign, work with me here. Okay. Now here's the trick. I take the polynomial, and any term that has an x in it, I'm going to bring the exponent of the x down into the front. So, for example, I write down whatever's already there. I already have a negative. Boom. There's no coefficient, so nothing goes there. But this 2, whoops, stop it. This 2 comes down in front, so I get a 2 now. And I rewrite the x. The x, whatever the exponent was, I gotta change it. Let's go with black here. There, that's easier to see. Okay, it was a 2. Now it's going to be 2 minus 1. Whatever it was, subtract 1. That's what you do. You just subtract 1. Okay? Then I have a plus. Put the 9 there. Well, here's a problem. I have no x. But really what you're doing is there was an x there. It was just an x to the 0th power. Like that. You can see that. So when I do my little trick, it brings that 0 down in front, and I end up with 9 times 0, which is going to go away. It ends up being 0. When I try and do, well, never mind. It doesn't matter what I do. I have something times 0, it's gone. So that whole term is just gone. That will also always happen with a constant. If you have a constant and you derive, it just goes away. It's gone. So what I end up with is the derivative of this function, dy dx, is negative 2 times x to the first. X to the first is just x. That's it. This is the derivative of this parabola. Now how we use it is to find slope at point x. I put in whatever x value I want to find the slope at that point. So I said I wanted to find the slope at negative 3x, where x is negative 3. That means that the slope at negative 3 is the slope at x equals negative 3 is negative 2 times negative 3. I just put the x value in for x, and I get the slope. The slope is negative 6. Boom. Done. Oh, I'm sorry. Positive 6. What the hell? Sorry, guys. Okay. Positive times or negative times a negative is a positive. Okay, and we go and check that. Just looking at the graph, I know it's got to be positive because it's going up at that point. It looks fairly steep. Plus 6 looks pretty good. If I were to estimate using that original green line that I drew as a tangent, let's just take that point and that point. Looks like I'm going from about, well, if that's 9, I didn't do a very good job of scaling this. That looks like it's about negative 4 up to about positive 5. So it's like a rise of 9. And then I've got a run of like, gosh, it's like 1.5 or something. I don't even know what that is, and I don't have a calculator handy. Anyway, it's probably something in the general vicinity of 6. You guys check it and tell me what it is tomorrow. I'm going to stop there for now. Just remember the trick for polynomials. There are other tricks for other functions. I'm going to give you a sheet of those, just print it out for you. Just tricks to remember. We use polynomials a lot, though. Mostly polynomials, and since it's such an easy trick, yeah. Anyway, that's the end of part 1. We're going to go on to part 2 in just a moment.